right, so let's continue. Good. So like I said, we moved the Proline part this year from the second part of the practical. It might be in the third one, but for now you're safe with it. But you will have to do the 2D texture mapping as part of the practical assignment, which is, like I said, the mapping of a 2D texture onto a 3D object. So the intuitive idea behind it is not this carving an object out of a structure, but to take a structure and kind of glue it onto an object. And the question is, of course, how do you do the mapping between a 3D object and a 2D texture? And of course, we could do this, or the approach to this is that it's quite related to or similar to this lookup approach that we have with this lookup table in 3D. Only now we are a little more flexible. Like in 3D, we only discussed it in a way of this tiling approach, that we create these tiles. Now we are more flexible. For example, we can make a perfect fit. Like, for example, if you have the map of the world and want to map it onto a sphere, of course, you do not want to have a tiling, but you want to have a perfect one-to-one mapping between the map and the sphere. Or you might have a situation where you only want to map parts of a texture onto an object. So we need some sort of mapping. The idea behind it is the same, using a lookup table, but the mapping is a little different. So let's look at a couple of geometric objects, how we can map them. For example, how can we map, like I said, a world map onto a sphere? So the problem here is, of course, here we have a map with 2 dimensions. So again, we call them often the texture space, which is U and V. And here we have a 3D map, a 3D object. So we have 3 dimensions. How do we map a position on a sphere onto a 2D position on the image? Well, if you remember how we defined a sphere, there were different representations, and one of them was the parametric representation. And if you remember, one of the key characteristics of the parametric representation is that it uses 1 parameter less than the actual dimension. So in this case, we only need 2 parameters to describe a point in 3D. So we can have an easy mapping by looking at the parametric equation. If we look at the parametric equation, we have the 2 parameters theta and phi that control our point on a sphere. Now we just have to make a mapping between those 2 angles and the xy or the uy coordinate that we have on our 2D map. So that means we first have to calculate the angles, which we can do with the inverse of this trigonometric function. Arc cosine is the inverse of the cosine, and arc tangents is the inverse of the tangents, of course. And the tangents is defined as the sine of x divided by the cosine of x, which is if you transfer this here, you will see that you will end up with the vector, the angle phi for that. So this is just a straightforward transformation. And then we have to do the mapping between the angles and the vectors here, but and the 2D coordinates here. So the 2D coordinates are, of course, defined by the size of our map. So this is the u and the v coordinates with the size of the map. But the tangents and the phi are also restricted. Like if you look at the sphere, of course, they are restricted by 360 degrees. So you also have here for the phi and for the theta, you also have a limited size here. So you can also think about this as a 2D rectangle. And then this mapping just becomes a straightforward window transformation like we had in the very first tutorial. And if you do that, you will see that you end up with this equation here for the coordinates. So if you want to calculate if we have a point here that is defined by the angle, you can calculate the corresponding texture value here from the texture map by using this relationship. So that is pretty straightforward because we have this parametric representation. Now, if we think about triangles, which is of course the most important geometric shape that we have in graphics, then the situation is also quite simple because a triangle is a 2D object basically in a 3D space. So we can just straightforward map all the corners of the triangle to some points in our 3D texture. I should have changed the color, sorry for that. So we just map the colors to here. So for example, here we have 109. So if this is our UV space here, 0.1 is here, 0.9 is here. So this point here is mapped to the corner here. Then we have the other points also mapped here. And then we can calculate for each point here with the mapping the color here. Or we could, of course, just calculate the vertices and then do an interpolation between them. And that, I hope you remember, that can be done very easily with barycentric coordinates. If we represent the triangle with barycentric coordinates, so by using the corner, the vertices A, B, and C, and then if we describe a point in the triangle, for example, here or here, with this form, we can do a linear interpolation quite easily by changing these parameters here. And if we do the mapping, then of course we can also do the linear interpolation very easily in this texture space, in our UV coordinate space, by just using the correlated vectors for it. So A becomes UA and B becomes UB. Actually, it should be vectors. Vectors? Yeah, of course. Yeah, okay, here you see it. Yeah, and then we can calculate them by this modifying the parameter here. So that is pretty straightforward, and you see here the definition of how we do the mapping is open to us. We can do it, for example, if this is our texture, we could say, of course, we map the triangle like this, or we could just map it like this, or we could map it in a way that we can do some very strange things. We could also do it in a way that we map it like this, which means we will probably have just a line pattern, although here we have a checkerboard. But if we make the triangle very small in the mapping, we could produce these lines here. So we can do all kind of things because we can put the image on the texture in any kind we want. We just have to define it some way. Good. Yeah, but of course we have then the same problem or the same situation that we had before. If we have a point here and we put it here, we have a point into a texture array which is defined by its corner point, so that point might be in here, and then again we can do a bilinear interpolation like we did in the previous case, that we do not just take the closest one, but we can do a weighted sum of all the surrounding points or color values that we have around it. And also another thing that because we have this random mapping, we can also of course make it in a way that this area doesn't even have to match the whole triangle. So for example, the texture doesn't, no, the triangle doesn't have to be completely in the texture. So for example, if we have a triangle like this, a huge triangle, and we have a texture that has, I don't know, a flower, for example, we can of course take this texture, that doesn't work, and map the triangle in a way that the flower is in the center of the texture. So the texture can go outside of the triangle like we already have here, but also the triangle can be outside of the texture. It just depends on what we actually want to have. Good. Now I said at the beginning, mapping textures to triangles is easy because we have a triangle is a 2D object in a 3D space, so the relation between the 2D texture and the 3D triangle should be straightforward. That is not completely true, of course, because the triangle is a 2D object, but it has an orientation in a 3D space. And that means also, of course, the perspective changes. So if you have, for example, a checkerboard and you tilt it, the tiles in the distance become smaller because we have a perspective view. Now, if you do a straightforward mapping of the corners like I just explained it, you will, and then calculate the values with the linear interpolation, then you will end up getting artifacts like you see it here in the center, where we basically map these two triangles to the two triangles here. And then you see, of course, this doesn't look correct from the perspective, but this would be correct. So we will talk about perspective projection later, which is why I will not go into the details here. I will not cover the theory behind it, because it is also supported by modern hardware. You don't have to calculate this, and if you do it with hardware, the hardware already automatically considers this kind of, or the API already considers this kind of perspective transformation, and then does it aligns it appropriately. If you're interested in a theory, you can read the related chapter in the book, but I will not cover it in the course because it goes too much into the mathematics, and like I said, we haven't covered perspective projection yet, so it's even if I want to, I couldn't explain it right now. Good. Another thing that is important for the practice to know in practice if you implement texturing is this so-called MIP-mapping. The problem with these textures is, of course, depending on the size of the texture, if you map a small texture to a very large object, you have to make it larger. That means you have to map one pixel or one single texels to multiple pixels, or the other way around. If you have a large texture and put it on a very small object, you have to decrease the size. Now, if our objects would always have the same size, we could pick textures that have an appropriate size. That wouldn't be much of a problem, and then we would always have some sort of a more or less perfect match. But of course, if we have an interactive application and we move, for example, objects, then if the object moves further away, it gets smaller. If it comes closer, it gets larger, and then the texture gets blown up, which could create artifacts, or it gets scaled down, which is not a problem in terms of quality, but is a problem in terms of performance. So, for example, in the extreme case, if your object becomes so far away that it just becomes 1 or 2 or 3 pixels, then mapping a huge image onto it, you basically have to consider all texels on the texture to decide what color you give those 3 pixels on your object. And that is, of course, very inefficient if you think about models with thousands or hundreds of triangles. And what we do with this in practice is that most APIs support this so-called MIP-mapping, which is basically just creating a set of textures at different sizes, and then the hardware, the API, automatically picks the one that is the appropriate size for it dynamically when it renders the object, depending on the size of the object, which depends in turn on how far away it is from the observer. So if it gets further away, it gets smaller, then we choose a smaller texture. If it comes closer, then we choose a larger texture to avoid these artifacts that you get when you blow up an image with a low resolution to a higher number of pixels. Good, but this is again supported by common hardware, so we don't really have to care about the details here, but it's important, of course, to know, and it's important to do this then in your implementation. Good. So so these are the main 2 approaches for texture mapping: 3D textures and 2D textures. But of course, there are also other kinds of variations of it, and I will talk about 3 here now, but I will only talk about the basic idea of it, because one of them, the bump mapping, is actually also part of the practicals. It's one of the bonus assignment, although there it's called normal mapping, depending on which source you look. They call it sometimes bump mapping, sometimes normal mapping, or usually they call it normal mapping as a more general term that includes bump mapping and other kinds of mappings, but it's pretty much the same. So the idea is so far we had textures that basically represented color, but of course we can also take textures and have them represent something else that we put then on our object. And let's start another way. If we have an object and that object has, for example, a rough surface, even if the object has the same material and the same color, of course the surface looks different if we look at it, because the light is reflected differently, and the light is calculated by a normal vector. So you see it, if you illustrate it like this, you see it. If you have a flat surface, then the normal vectors all point up, but if this surface is kind of has a more bumpy, or in this case it's a very regular structure, it's like this sine-shaped structure, a very flat sine curve, then you see that the normal vectors of course change, which means also that the light calculation at these points here change a little bit, which is why we see the object, see the structure of the object when we look into it. So if we want to model this, we have to calculate each normal vector and each color at each point individually. So that is of course not very efficient. And a trick we can do is we can use a texture map, not to calculate the color, but to represent normal vectors and then paste the normal vectors onto our object. So it's basically a trick to create the illusion of this bumpiness by taking the normal vectors, pre-calculating the normal vectors, how they would look like, and then replacing these linear, these correct normal vectors with these wrong ones. But then if you calculate the light here, it calculates the light value in the same way as it is here. And if you just look straight at the object, of course you will see the very same thing in both situations here. So if you look at it from that side here, then of course the color value here will be exactly the same as the color value that you calculate here, because here you used the same normal vector and you used the same color value that you have on this pixel and the material. So this is the very same value. So you can create the illusion that you actually have here, this rough or bumpy surface, by just modifying using a wrong normal vector, and this normal vector you can store in a texture that you then map onto the object. The only problem of this is, like I already said, if you look at it from that position, if you straightly look at the object, you see the same value here. But if you look at it from the side, so for example here, of course if we just change the normal value, we do not change the value of the actual the shape of the actual object. So there is still a value here, whereas here, for example, you see there is a little hole here which does not appear here, because here we just modified the normal vector. And that means that if we look at for example a situation here and compare it with here, it doesn't look the same, but it looks very realistic. This on the left doesn't look less realistic than the shape on the right, but it looks unrealistic if you look at the actual silhouette of the shape, because here it's really flat, not flat, but a straight line, whereas here you have this bumpiness. So, and this is the major problem with bump mapping, that if you have an object very close that you can also see the silhouette, then you see that it is not the real mapping, not the real object, but it's basically a fake approach to create only the illusion of structure. And one way to solve this is to use so-called displacement maps, so another texture map, but now we do not interpret the vectors that we have as normal vectors, where we change the normal to create a different light, but we use them to actually change the surface. So the values here that we have on our displacement map are not used to modify the normal vectors, but they are used to modify the shape. So here we go down, here we go up, here we go down, and that means we create this, I don't know why this is not connected, we create this shape here, and then we can calculate the normal vectors, and then we get the same values as with the bump map when we look straight at it, but also when we look from the side we get the correct shape because we modified the shape of the object. So you see here that this creates more realistic results, but of course the problem with this is we then really have to calculate each normal vector again at each position, whereas in the other case we have the normal vectors pre-calculated and stored in a texture map. So the bump mapping is way more efficient than the displacement mapping. The displacement mapping takes a lot of calculation time, but it produces more realistic results. Good. So another way to use texture maps to create realistic images, so-called environment mapping, which is used to create reflections of the environment in an object. So what we do here is we do not paste the texture on an object, but we paste the texture around the object, and then we take from a position on an object, we see how it reflects when we look at the object from where it reflects, and then we put the color of the texture that it hits on the surface of the object. Let's look at this image here that explains it quite nicely. So we have an object here, and we place a texture around an object, like in a cube, for example. In game implementation, this is usually called a skybox, which is used, of course, first of all, to create the background of your scene, but you can also use it with environment mapping to create a reflection. And you do this by, like if you think about the light calculation, what we did for the light calculation, we have a normal vector, then we have an I vector, and then we set, depending on the angle that the light here has, if these two angles are the same, then we have for the Phong shading the maximum reflection, the maximum value, because this is what you would get in a perfect reflection. And this is exactly what we're using here. We take the I vector towards an object, then we have the normal, and then we calculate the perfect reflection until, and then we follow that ray until we hit the environment, and then we know this is the pixel that would be reflected here with the perfect reflection. And if we want to create such a reflection on our object, we just draw the color value from that reflection here on the object. So you see here how we can use texture mapping to create these reflections, not by putting the texture on the object, but by putting it around the object, and then creating the relation between the object by looking at where would the perfect reflection come from, and then use the texture value to create that reflection here in the object. Good. So yeah, like I said, this is just a general overview of the additional alternative approaches. So that's about it with the texture mapping. We have enough time, so I can show you also something. Today we had the 6th lecture, which means we have half of the lectures, if you don't count the special lectures like the introduction to the practicals, but the lectures with the content that count for the exams. We're at the number 6, so we already are halfway done, which means I'm usually showing a little clip now because we have already showed a lot, achieved a lot of things, so it's also, I think we deserve a little break. All right, so one of the reasons why I'm showing this is, like I said, we're at halftime now, and we did so much theory and dry stuff that I think you also deserved a little a break. But the other reason is, of course, halftime. That also means midterm exam, so you also have to pass an exam, and I hope you will do a little bit better, or much better. So just a few notes on the exam. In case you still haven't noticed it, it was moved to Friday. I realize there are some people who still are not aware of that. So it will be on Friday next week. Just a regular announcement. Check the website. It's all on the website also, but just a reminder. Come in time, bring a pen, bring your student ID, and know the answers. That's all you need. There are no utilities allowed, so you're not allowed to use books and notes or other stuff. Just a few more minutes. I'm almost done. And yeah, content-wise, it only covers lectures 1 to 5. So the lectures that I have given, not Marise's lecture, that was for the practicals. 1 to 5, that's all till last week, the transformation matrices. So not today's lectures. I have to bring that before the midterm exam. Also, the next lecture will be before the midterm exam because you need the information for the practicals. But content-wise, it makes more sense to have the first 5 lectures, which is the mathematical background that you need for graphics in one exam. So, which is why I'm restricting it to those 5, and also the first 3 tutorials. People always ask, how should we prepare? If you follow the lectures, textbook, and the exercise from the tutorials, I think you should have not a problem passing this exam. If you want to prepare more, there are also on the first website at the entrance, you see at the bottom links to previous years where you can find the old exams from previous years. I might change them, of course, a little bit in style, but it's a good preparation. I think also AS Quadrat has them. I always send them to them. I think they have an archive. So yeah. So just a summary, like I said, today's lecture and the next lecture next Tuesday will not be part of the exam, but of course part of the final exam, so it's important to follow them as well, and you need them for the practicals. Thursday there is no lecture because there's a holiday, of course, which means also there is no tutorial on Thursday, so the people who have their tutorial usually on Thursday should go to the tutorial on Tuesday. The people who are at the tutorial today do not have to go on Tuesday. If there is enough space, you are of course welcome to come and ask questions because it's in the week of the exam, but it depends on how much space we have then. Thursday there is no lecture. Then next week also, because the original exam was originally scheduled on Thursday, and I don't think it makes sense to have a lecture with new material one day before the exam, so there is no lecture. Also, there was no tutorial scheduled, but I have to talk to Peter. If he has time, he can also probably give a tutorial. I have to talk to him. But I have to wait because he's not here this week, which also means that today there is only one tutorial, which I do, but I will do it in room 61. So if you go to the tutorial today, please go to room 61 because Peter cannot be here this week. Good, and next week, like I said, the midterm exam, don't forget that. All right, then see you again next week.